Today, I'd just like to have a quick look at some logical operations using some binary values and how we might use them in practice to build some circuits that we've likely already seen. In this example, we're going to test for equality using a standard disjunctive normal form definition of equality. We're going to do that bitwise for 2 words, and yeah, we'll have a wee look at that. So you can see up here I've loaded in 2 words. I've got some ones and I've got other ones. So this is going to be defined by FO, FO, and so on. But what this really means is it's the repeating pattern of 4 ones followed by 4 zeros followed by 4 ones. Now this is because F is of course equal to 1111 as a hexadecimal number. So this is when all the ones are set. So we have some ones, and our other ones is the exact opposite pattern. So it's quite clear that this is the logical negation of this, and vice versa. You could negate one to get the other. So I've loaded these into memory, and let's just test some basic logical operations on these before we get on to testing for equality. So if I AND these, you would expect that I'd get all zeros back because they always mismatch, so I always have at least 1 0 when the other value is 1. So let's see if that is the case. So let's do A0 with A1. Let's assemble that and run it. And yep, as you can see in T0 we have all zeros as we would expect, so let's go back to this. Now the opposite is if I do this with an OR, or an exclusive OR. In that case I should get all ones back because there's always at least one of them always has one set when the other doesn't. So let's do OR and see if we get all ones. And indeed we do, we get all ones, which is represented by all Fs all the way down. So this is just basic stuff, it's nothing too wild, it shouldn't be too surprising to you, but let's have a look at how we do something a little bit more complicated. So if we want to do this, then it would make sense that we start by doing the AND of X and Y. Actually, we're not using T3, we're using A0 and A1. To help if I mentioned registers that are actually in use. So let's test for equality. So it makes sense that I would do this first because this doesn't involve negating the values. So let's do that. So the AND of these values is going to be stored in T0, and it's going to be, as we saw earlier, A0 and A1. Now we expect that that's going to be equal to 0, but that is equivalent to our X and Y up there, so that bit's done. Let's mention the register it's stored in, just for the sake of posterity. And then we can get on to the negation. Now this is something to be wary of in MIPS. We have negation and we have not. Now remember, in 2's complement notation, if we want to negate a number to get it from negative to positive or positive to negative, we flip the bits, but we also add 1. So negation will flip the bits and add 1, whereas not will just do a bitwise inversion of the word you give it. So make sure not to mix them up. So I'm going to store these in the registers that they are already in because we don't need to use the values anymore because we've already done the X and Y part. And we'll do the same for A1. So that should be relatively straightforward. Actually, let's give these comments because I should practice what I preach when I'm always telling you to do this. So in this case, A0 is going to be equal to naught of A0. And here we have the same, A1 is equal to negation of A1. So far so good. So now we need to AND these values, and we just do it as we did above. We'll store this one in T1, and we'll do A0 and A1 like that, and that is equal, that is going to say that T1 is equal to not X and not Y in this case. And then we just need to do the OR. So this is going to be, let's store this in T2, and it's going to be the OR of T1 and T0 like that. So let's assemble and run this. We would expect to get zeros, and we get zeros. So let's test this to see if this would work with something that is actually equal. These are most certainly not equal, but what we can do first is, before this starts, we can apply the not to a not. And that should flip the bits so that we get something that is equal. So that's just flipping over so that f0, f0 goes to 0, 0f, 0f, so on and so forth. These are zeros, just can't type. So let's compile this, or assemble this, run it, and see if it works. So there you go. T2 is now in fact all ones. Now normally if you were doing this you would just get a single bit, so you would just get a single bit as a response. You get 1 if they're equal, 0 if they're not. In this case it's bitwise, so we get the whole thing compared to the whole of the other thing, so we'll find out where each bit is equal and where they're not. So we could have something a little bit more complicated. So actually let's do that and see what happens. So let's comment out that line, and let's say that this is going to be a more complicated word. Let's say it's a C, D, not D, and 3, and let's do something similar up here where we have 1, 6. Oh, it's too long now. And D, let's do an F in here. So now here we have more complicated words than we did before. So let's assemble this and see how our logic test works. Now you can see here in T2 we have a much more complicated value than we did beforehand, and that's because it's it's applying it bitwise. So this represents the binary number that tells us which position is equal. So we don't just get the 1 bit telling us if the whole thing is equal or not. We get all F's if it's all equal. Otherwise we get a hexadecimal number that we would have to unpack into binary to understand which bits are equivalent. So that's everything I wanted to go over today. I hope this was useful for you. If you have any questions about anything I covered here today, please do let me know. Thanks.